This is the SixSigma.org 3-factor DOE template that's built in Excel. What it permits you to do is look at a design of experiments with 3 factors at 2 levels, so a 2 to the 3 factorial design. And the first thing we do, and as with all our templates, when you see yellow coded cells or yellow colored cells, that requires an input. So first thing we do is identify the factors. I've got factor A, B, and C here, and I'm going to use the helicopter as my example, the paper helicopter that we've seen in another module. And the first thing I'll do here is identify the wing length, so that is one factor. And I've coded them here as high and low. As it turns out, there's a short wing and a long wing version of the helicopter. Second thing I have is the body height of the helicopter, coded as well as 1 or 2. This is called a coded design, by the way. And the body height, as you can imagine, then is both a short and a long body. And then the body width is the third factor, with a short body coded low and a long body coded high. Now, down below is because we've got a 2 to the 3, we actually have 8 different combinations. So, and the way I get that is, of course, 2 by 2 by 2. So 2 by 2 is 4 by 2 is 8. So 8 different combinations of wing length, height, and body width. And here they are. Now I've selected in the template at least a random order. What I could do, and perhaps you'd like to do, is I could number these sort of 1 through 8. And then what I'm able to do is, rather than run them in this particular order, what I would do is go over to my random number generator and put in here a number of unique numbers I want is 8, and they'd be anywhere from 1 to 8, because that's of course representing each of my different configurations. And then I could run them in this order, so configuration number 3, number 4, number 6. So it would be, let's say this is configuration 3, and then 4, and then 6, and we could run them in that order. But for now, because I haven't done that, but certainly that is ideally what you'd like to do. Randomization is very important. But for now, I've picked a random order, and you can stay with this if you'd like. So the first run that I have is wing length 1, which is the short wing length, with a body height that's also short and a body width that's narrow. And I want that configuration helicopter, and then I do my helicopter drop and I record the time, 1.3 seconds. The second run that I want to do is a different helicopter. In this case, it's wing length that's long with a body height that's short and a body width that's narrow. And I take that helicopter and I drop it, and let's say I get 1.8 seconds. And then for my third run is a different helicopter. Again, I have a wing length that's 1, a wing length that's short, a body height that's long. Remember, these represent both short and long. In the case of the width, it's narrow and wide. So I've got a body height that's long and a body width that's narrow. I take that helicopter and I drop it, and it's 1.6 seconds. And I continue to do that through my 8 runs, and I record my 8 drop times here. Now, if we have replicates of this, I then come over into the column. I go back to the first configuration of a 111, drop it, and now I record the time as 1.7 seconds, say. That's what it is. And then I go to configuration number 2, or run order number 2, get the configuration and record the time here, and so forth. So these numbers across the top represent the replicates. This will be my first run. This is normally called a first replicate, although in some of the commercial software the first run is actually called a replicate, so just be careful when you're talking about the number of replicates. But for the purposes here, this is my first run, and then my first replicate, and my second replicate, and so forth. And I record my times here. And then as I look down, the first thing I'm going to come to are the effects. And so these are graphics that tell me to what extent effect A affects the flight time of the helicopter when I go from my low value of A to my high value. Now remember, A was my wing length, and so as I change my wing length from short to long, you can see how it affects my flight time from somewhere in the 1.48 or 1.49 seconds to about 1.75 or 1.8 seconds. On my effect B, and if I go back and look at my factor B, it's the body height, and it would seem to indicate that as my body height goes from narrow to wide, the wider my body height, the lower time it takes for the helicopter to drop, which makes sense because I've got more, there's more structure, if you like, to the helicopter, so more weight, which, and then intuitively you would expect it to take less time to drop. And similarly for the body width. Now, one thing you look for here is the steeper the slope on the line, then the greater the effect on its impact to the flight time. So in this case, A has somewhat of an effect because it's got some slope to it, although you can see here that there's very significant slope to factor B and very significant slope to factor C. Moving down, I now look at the interaction. So it's the interaction between A and B, AC and BC, and you can see it's A and B for the AB interaction, and then AC for the AC interaction. And what you're looking for here is that to the extent that these lines do not cross one another and/or are parallel, if they're parallel, then there's no interaction between those two factors. And you can see in the case of AC, there's very likely, at least not within the inference space that we're looking at, there's no interaction between A and C. And there could possibly be some interaction between A and B when you've got A is in the low configuration. So you remember A is the wing length, and we're talking about short wing length. So if I come down here, when the wing length is short, it would seem to have some effect as an interaction with B. We've covered AC, and similarly on the BC interaction, when B is when it's in its low factor configuration, and that's the body height. So when the body is short, it seems to have some interaction with the body width. And that's how you read those interactions. Now, so that's the graphical version of the interpretation. If you come down here, we look at the Anova table. The first thing I have to do is select confidence level. So I'm picking 95% confidence level here. And then the Anova table will tell me factor A is significant. Factor B is also significant. Factor C does not seem to be significant. And none of the interactions are significant as well. Now, you can verify that through the graphics. So we see that A and B are significant, but C is not significant. It would seem to indicate here that C is significant, but based on the Anova table, it's telling us that it's not significant. This gives you a prediction equation. And what you can now do then is, using coded values, you can predict the drop time of the helicopter based on a given configuration of A, B, or C. So perhaps we want to look at a wing length that's long, body length that's long, and maybe a body width that's wide. And so for a configuration of 222, we might expect something in the order of 1.46 seconds to drop. And let's go and just look at that particular configuration and see what the drop times were. The model is predicting approximately 1.5 seconds. If we look at configuration 222, there's one right there. You can see it was about 1.5 seconds, and we should have another one here as well. And oh, I'm sorry, we don't, because actually this is the replicate right here. So they were both 1.5 seconds. The model is predicting about 1.46 seconds. So that's the template in terms of a 2 to the 3 full factorial. And the helicopter is a great example of teaching the elements of, or the principles of the DOE. So I would encourage you to do the helicopter DOE, and when you're doing it, have fun.